All right, so this section in AP Calculus AB and Calculus 30L is Riemann sums. Now, we've talked a little bit about this, and this is probably not going to be totally brand new to you. There will be some specific stuff later that will be brand new. But Riemann sums help us to approximate an area under the curve. Now, for you guys know about integrals already. We talked about integrals. We are kind of going back here. Riemann sums is the basis for integrals. So if you're watching this video and you haven't seen integrals yet, this is the precursor to that. And this is where integrals come from. So at the end, I'm going to connect Riemann sums with integrals. Okay? So this is a little bit of a foundation, a basis. Remember when we did derivatives, we did all those rules? Okay? The limits were the foundation of the derivative, right? The definition of a derivative. So this is sort of going back to the definition of an integral, really. Okay. So where are we going to start? Well, we're going to start with the fact that if you have a velocity versus time graph, like this one, this is some object traveling at 75 miles per hour. So I'm just going to put miles per hour over here. And traveling from 7 hours to 9 hours. So this is hours down here. Okay? Now, what is the significance of this area here? Well, if you think about this as an area, you would multiply the length here, hours, and it's going to be 2 hours, times the height, right, which is 75 miles per hour. If you multiply those, you get 150 what? What's miles per hour times hours?
Mile.
Yeah, look at this. See how the units cancel out there? You're left with miles. So if you think about it, if you're traveling a certain speed for a certain time, you're going to be able to go a very calculable distance, right? So that's what it is. So the area under a velocity versus time graph represents distance traveled. Okay, and that alone makes this area very useful, very important. Okay, now let's move on here, and let's say we didn't have an area that was a nice rectangle like this, but let's say we had an area that is a curve. This is part of a parabola, right? From 0 to 3. Let's say the velocity here. Okay, so this is still velocity here, and this is still time. But this is an object that is, its velocity is, its path is moving like this. The velocity is changing over time. It's speeding up, isn't it? And so if we have something like this, we could approximate the area under the graph. And we talked about average value of a function already, right? So you might be thinking about that. Again, this is still a precursor to that because that has to do with integrals. So how could we estimate this area? We could use the rectangular approximation method. And that simply states that, doesn't matter what kind of graph we have, like the function itself, doesn't matter what it is, if it's curved or whatever, we could set up a series of rectangles and we could add the areas of those rectangles all up. And that would be a half-decent approximation of what that area under the graph would be. So let's say this was the velocity, this was the time, and I wanted to know how far, we went. Well, the area under the graph from 0 to 3 here, okay, if we were to consider this area, that would represent the distance traveled. That make sense? Even if you had a graph that looked something like this, and it was really, really strange, right? Something like that. The same thing. What you could do is you could split this up into intervals. They don't have to be the same width, but that's kind of nice, and we're going to be talking about intervals that are the same width in this lesson. And so you could estimate the area by using, rectangles. Now, the rectangles themselves, do you see how, I'm going to zoom in here, do you see how these rectangles, the height of the rectangle happens to be kind of halfway between this little partition here? Okay, so each of these would be a little section or a little partition. And the height would be where the midpoint of that rectangle is. See that? So that's a pretty good guess there, really, because we're overcounting some of this area, but we're also missing pieces. So we're overcounting and missing, overcounting and missing. so it kind of balances off a little bit, right? And so that's where we talk about different ways of doing this. If I put rectangles and I use the midpoint of the partition, right, it would look something like this. So you see kind of how this is working? And so the sum of the areas of all of these rectangles would approximate, I'm getting off there, but they would approximate the area under the graph. Everybody see that? So RAM is the rectangular approximation method. Now, we talked about the heights of these rectangles being midpoints, but there also is this is going to be a little bit easier to calculate actually. Instead of calculating the midpoint, we could calculate where the heights are actually on the graph, okay? And they're actually part of the rectangle. So instead of calculating, hey, where's the midpoint of this, and then calculating kind of where that is on the graph, we could just use either the beginning point or the end point of the graph and use that as the height. And so we have different rectangular approximation methods. We have LRAM, MRAM, which is the midpoint one, and we have RRAM. So this is left. So the left part of the rectangle there. So LRAM is left rectangular approximation method, and that's where the left side. So down here at 0, okay, we have a rectangle that's just a height of 0. Then we have this point there, this point. You see how that's the left edge? Okay, that's LRAM. The MRAM is where the midpoint is, and we've talked about that. That's the one we just kind of talked about, midpoint, MRAM. And then over here is RRAM. So that's where the right side, or the right edge, is taken as the height of the rectangles. You see that? Now you can probably guess that, as we mentioned, the midpoint looks to be the best approximation. This one looks way off because we're missing a whole bunch of pieces. This one looks way off because it's an overestimation by a lot, right? And so you might ask, why do we even consider that? Well, I want to show you a couple things here. And the two things I want to show you is this, is that we would be accurate in saying that the LRAM, if we added up the areas of these right here, and it's important here, the width of each partition times the height. And we have a 0 height here. Here we have, the first one we have 1/2, and then and so on, 1, and then 3/2, and so on. These are the different heights here. And if we add up all of these rectangles, we get this for an area. And this is actually a little bit low because we haven't counted a bunch of things. Over here, mid-RAM, or middle RAM, this is 8.9, and right RAM, we've overcounted, so it's definitely higher. All right? So these are the different rectangular approximation methods, LRAM, MRAM, and RRAM. Now, this part is important, okay? And I'm going to zoom in just a bit here, just to focus on this for now. Okay, the whole point of Riemann sums is the width of the rectangles are important, okay? If we have a really wide width for the rectangles, we're going to be either overcounting or missing like big chunks, right? But what happens if those rectangles become really thin? Or we have more of them? So this chart says this. If we had 6 rectangles, this would be the estimated area, which I think is what we have just above. So with 6 rectangles, as in the diagram, is that right? 1, 2, 3, 4, 5, 6. These are the areas for the 3. 6.8, 8.9, 11. But as the number of rectangles gets larger and larger, so think about what it would look like if there was 1,000 rectangles. They would be super thin, right? Super, super thin. And then look what happens when we use LRAM, MRAM, and RRAM. Look at the difference. It almost becomes nothing, right? And you can probably guess if we use 10,000 or 100,000 or 1,000,000, these numbers would approach, the same value. And so as I zoom back out here, this would be an example, kind of a rough example. I tried to draw this earlier but didn't do very well. But let's say that there's 24 in here, okay? 24 rectangles. And let's say this one, there's 100, okay? So do you see how we're getting very, very close? the little bits that we're missing, if this was an LRAM, the bits that we're missing are super, super tiny, right? Like virtually nothing. And versus, above, or even with this one with 24, right? So as the number of rectangles gets more and more and more, the width gets smaller and smaller and smaller, and the area of all of those added up gets closer and closer to the actual area under the curve. Any questions so far? Yes?
Why is MRAM not the little number of LRAM and RRAM?
Sorry, why is this number not exactly between these two? Mm-hmm. Okay, well that's a pretty good question. It depends on the shape of the graph, I guess, right? So we may be counting a lot extra with the with this one. See how much extra here maybe doesn't match up with how much we're not counting here exactly. Okay. All right, so this is almost 7. That's just a little over 11, and this is almost 9. So the actual average you said was, you figured out was 9.1. Okay, so that's pretty close to. It looks like 9 is going to be our actual. Okay, so the average between these two, that doesn't necessarily guarantee us that we're going to have the closest to the actual value, but it's going to be pretty close. This one you see is the closest. This is what seems to be the value that these two are converging to. Okay, so it's not always the average. If it was a straight line, maybe the average would be more appropriate, but because it's curved. Okay, so let's just continue on here. Now I think he might have pronounced his name Georg. I didn't know him, wasn't alive this time. But George without an E usually is Georg. So I'm going to say Georg Reimann as his name, and here's a picture of him right here. And so he's the one that came up with this, and more specifically, he came up with, he's using this notation here. Now I kind of zoomed in on this notation down below, so let's just kind of get this in the picture here. All right. So what does this say? What does this mean? This really is the essence of Riemann sums, and we'll just get this out of the way. I'm really not impressed with the notation that the publishers are using for the function. Just to be upfront, I'm not too happy about that. Okay, it's a little distracting for me. I'm not sure for you guys, but anyways, they could have used some other letters, I thought. However, let's just go through this anyways. Okay, someone was really upset when they were doing this at one point and came up with this notation. I'm not really sure. All right. So this, anybody know what letter this is right here? It's a letter.
Sigma.
Not theta. Sigma. It is sigma, yes. It's the uppercase sigma in the Greek alphabet, and it means in math and science, it means summation of, okay? It means summation. So that means we're going to be adding things. It's a sum. Now, this is the function, and C sub k is just basically, it's either the value at the left endpoint of the rectangle, at the right endpoint, or at the midpoint, whatever we're using there. So it's just the value of the function at a certain kind of arbitrary point. It would either be at the beginning of each little subinterval, or it would be at the end of each subinterval, whatever. This here is the size of the width of the rectangles. So it's the width of the subinterval. Okay. So if we go back up here, right, the width of the subinterval would be, this would be delta x, the width of one rectangle, delta x. Okay, and this would be f sub k right here for our RAM. And the limit part, now we think about this, remember, as those rectangles get smaller and smaller and smaller, it means that we're fitting more and more into the interval, right? And so as the limit of the number of rectangles in the subinterval, as the number of rectangles in the interval, becomes close to infinity, that means those little rectangles are getting slimmer and slimmer and slimmer, right? And approaching just the continuous area underneath the graph. So this says that the limit as the number of rectangles basically approaches infinity. If we add up, okay, the number of rectangles, okay, the area of the first one, and all the way up to the area of, an infinite number of them, then we will get the area under the curve, or the definite integral, for those of you that know about integrals, right? The definite integral. So the more and more rectangles we have, the closer the approximation is. So this is basically height, right? Right here. And this is the width of each rectangle. And we're going to, as the number of rectangles approaches infinity, that's going to be equal to the total and exact area under the graph. And so for you guys, for our class here, we've talked about integrals already, so you do have an introduction to integrals. And this is a new identity here that we're going to be exploring further. But the definition of the integral basically is this Riemann sum. Okay, so this is important. The interval from a to b is not mentioned in the sum notation here, but the interval a to b would be separated into a whole bunch of different rectangles, right, into sub-intervals. So a and b aren't mentioned here. It's just how many rectangles, the width of each rectangle, and the height of each rectangle. So a limit of sums means integral. Here's the other neat thing, okay? Remember this integral sign? Remember when I talked about integrals? This is an elongated what? S. So look at this. Elongated S, sigma. Okay? It means the sum of, right? This is the height of each rectangle. This is the height of the graph at a point, right? This is the width of each rectangle, and this d of x can also be interpreted as the differential of x. Like that is just the difference between the two x values as we let them come closer and closer to each other. So really there's a lot of connection, the sigma and the function itself and this little differential there. Okay? All right. And you have any questions about that?
No, I didn't get the CK.
Okay, so the question is, where does the CK really fit into? And in your textbook, I didn't really see a diagram with it clearly on there. I think it's there somewhere. But this would be like a C sub K here, like this value that we're going to use for, well, maybe not that one. This one looks like it's a mid, but so the C sub K is like whatever value we're going to put in to find the height. So it's the x value that gives us the height of the rectangle that we're using in the Riemann sum. So here, this is C sub K. That's a C sub K. This is another, C sub K. This is another C sub K, and so on. And so they're the actual x values that you use to determine the height.
Then how do we know that which CK are we going to use?
Okay. Well, we're going to take a look at that. Okay. So, which CK are we going to use? All right. Before I get here, let's just talk about that a little bit. Okay. So here. All right. So where do we get our C sub K from? If we have two intervals, okay, then our C sub K is going to be right here. Sorry, that's supposed to be a vertical line. This is C sub K. Okay? There's just two. So if we're using LRAM, then here is the first rectangle, which is 0. Here's the second one. Okay? Not a good approximation, but that's our C sub K. Two intervals, we have one C sub K. So what happens if we, the C sub K depends on how many intervals we actually state. Okay? I don't know if I can erase it. Okay, good. So let's say we want 3 intervals. 1, 2, 3. 1, 2, 3. Okay? Pretend those are evenly spaced. Well, then we have C sub K1 and C sub K2. Or maybe this is C sub K1, right? And then 2 and 3, and then really 4 or whatever. So depending on what we're going to use. LRAM, there's 1. Boom, there's 2. Boom, there's 3. You see that? So we use this one, and this one. That's C sub K. So, of course, one more time, if we do this all again and we have, a certain number, let's say we have 10. Or let's say, let me just do this. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, pretty close. So then this is, C sub K1. There's C sub K2, and so on. 3, 4, 5, 6, 7. So the C sub Ks are just basically the separators of the partitions. Okay? And then you use whichever one you need to use. If it's LRAM, MRAM, really MRAM, there would be one in between here, right? Like that's MRAM. So for this one, here's MRAM. Okay? So that's where C sub k comes from. It just totally comes from, however many subdivisions that you have or partitions that you have. C sub k would be the dividers there. If you're asked to evaluate this sigma notation, then what you have to do is you have to add up all of the rectangle areas that are represented here. So for this one here, J is going to be, this is going to be our lower bound here, really. So we're going to have 0, so you got to put 0 in for J. So this is going to equal 100 times 0 plus 1 squared. I'm going to start with 0. Now the summation here indicates, we're just going to use whole numbers here. Okay, so 0, we're going to go to 4. Generally, it's a whole numbers. Okay, that's what this is, just whole numbers. So the next one is going to be where we put a 1 into J there. All right, so we get 0. We're going to use 1, 2, 3, and 4. That's what 0 to 4 is. Okay, and we're going to add them. There's the sum part.
How do you know, like 45?
With the sum, it's always whole numbers. Yeah, with the sum notation, it's always whole numbers. Yeah. The width, now, the interval width is going to be in here. Okay? That's what this sort of is. Okay? The interval width will be a piece that's in here. So you just have to do whole numbers here for the sum. It's kind of like the first rectangle, the second rectangle, the third rectangle, and so on. And this sort of function right here that you see, this big thing right here, it's going to be built in. So you can just use the whole numbers here when you evaluate.
So is the CK?
Okay, so the second one is 100 times what? That's 2 squared, so that's 400. 2 plus 1 is 3 squared is 9, so that's 900. All right, 1600 and 2500. So the answer here for this one should be, what is that, 5500? Okay? 55. Now, if this was a function times the width, it was some graph, this would represent the area. Okay? So that's how you use summation. So this one here, this one is going the other way now. So basically you're looking at this part and seeing if you can write it into sigma notation. So let's take a look at this. It appears that the function is going to be, like there's a repeated part here, right? And so the part that changes is the inside there. So it looks like this is 3 times something, right? Let's give it a t. And it's squared. You see that? Now we are adding up. So there's going to be a sigma notation here. This is going to be the function. And what are the n values, or the t values, I guess? T equals, okay, the first one is 1, yeah. And we're going up to, it looks like what?
500.
500. Okay, so here's some questions from your textbook. These are the ones we just did. This one right here, and this one right here. So you can work on any of those that you want. I'll give you your assignment in a bit. This one right here, so if you look at, again, limit of a sum is an integral. So writing this in integral notation, this part means integral. Here's the interval, and so that's where you have your integral sign 0 to 2, right? This represents the area underneath what would be a graph. Now this would be ck squared, so that's going to be some function with ck in it, right? And so what's the function? Well, it's ck squared, or just x squared. And the dx part would be like your little width of your rectangle, right? Remember the differential of x, or the little change in x. So that's the connection here, the limit of the sums and the integral. Okay? So again, where we see ck, just put an x. This part right here is integral. This is the limits of integration. And this is just dx. So yeah, it's in your textbook. Just give me a second. I'm just going to roll through. So there's going to be some more questions too that I'm going to get you to get and to do. And this is here's the textbook for that. So you can look at this video a little bit later if you want to go over some answers or do some extra work. Okay, so I think that's the end of my lesson there. And again, just wanted to basically connect the Riemann sums with the integrals for you, and that's an intro to Riemann sums. Any questions?